Okay, so guys, remember there was a previous substitute teacher and you were given some packets after the naming quiz. Now, some Hilly said we didn't work on it at all, right? You took the quiz and then, but those worksheets will help you understand this concept. You should try to do them. The answer key is on blackboard. And you can always come back and ask questions later. But let me briefly review what was given in those worksheets. Okay? Now, so we have electromagnetic radiation. All right? There are a whole set of waves starting from radio waves to microwaves, all right, to infrared, visible, ultraviolet, all right, X-rays, and gamma rays. All right? You can write it on top of that sheet, or it's right there. Daniel, remember you have the sheet? If you had done that, that's the order, from the lowest to the highest. You see the boxes? Okay. So, now, so if you were, these are waves, right? And you know how waves travel. And if I were to draw waves for this, I would draw them like this. All right? What does this tell you? All right? You know that when you go to a dentist, you need to wear a vest so that the X-rays don't harm you. Is that right? Yes. And it only penetrates your teeth. So you know these are dangerous. All right? So when the tsunami hit and the nuclear power plant broke down, the radioactive materials in Japan gave off what kind of rays? Gamma rays. All right? And they can cause mutation and things like that. Is that right? So why are they dangerous? Because they are high energy. They are high in energy. Whereas these waves are low in energy. All right? They are low in energy. Now, so this is, say you draw a wave, all right? This distance between two crests, so to say, is known as the wavelength. My board is not aligned. Let me align it. It's messed up. Okay? So the distance between two crests is known as wavelength. All right? This distance is the wavelength. Now, this is the amplitude of the wave. We're not going to be working with the amplitude of the wave, all right? We're just going to work with the wavelength. Now, wavelength is a length. Is that right? Yes. But then the length is really small. So wavelength is generally measured in nanometers. Wavelength is measured in nanometers. And what's the conversion factor between nanometers and meters? 10 to the 9 nanometers makes 1 meter. All right? So a lot of nanometers, right? Make 1 meter. So now, this is the wavelength. What is frequency? Wavelength is also denoted by Greek letter lambda. This is called lambda. That's how you denote wavelength. Just given the symbol, all right? The next thing you should know is what is frequency. Frequency means how often something happens. Is that right? How frequent it is. It's measured in units per second. So if you were standing here, all right? Say you were standing here. As you're standing here, how many waves pass you? Does that make sense? How many waves pass you is called frequency. Units is 1 per second. It's per second. Does that make sense? 1 by second is also called per second. It's also called hertz, or is abbreviated Hz. That's frequency. Okay? Now, let's look at these waves. What happens to frequency? What is the difference in wavelength here and here? As the wavelength gets shorter, what happens to frequency? Frequency gets higher. Yes. Okay, answer the question. Sorry, I thought you had a question. All right, so let's write the relationship down. So wavelength, as wavelength decreases, all right, or wavelength gets shorter, what happens to frequency? Frequency becomes higher, all right, or it increases. Are we good? Do we get this relationship? Wavelength and frequency are inversely related. How are they related? It's an inverse relationship. One increases, the other will decrease. One increases, the other will decrease. Okay? Now, we said this is the high energy end of the spectrum. What is the relationship between frequency and energy then? Yes, Daniel.
The higher the energy.
The higher the frequency.
Oh, the higher the frequency, the shorter the wavelength.
No. Connect frequency and energy for me.
Oh, the higher the frequency, the higher the energy.
Very good. So higher the frequency, higher the energy. So as frequency increases, energy increases. It's a direct relationship. Okay? Now, let's go back and let's answer some of these questions on your worksheet. All right? So this is the wavelength. Correct? That will be the amplitude. Correct? So, if you were to draw a wave that has a higher frequency, could you do that on your paper? Does everybody know how to do that? A wave that has a higher frequency will look something like this. Is that right? So who would like to attempt number 3? It's something we just discussed. Who would like to try number 3?
I can.
All right, go ahead, Natalie.
As the frequency of a wave gets higher.
Higher. If the frequency gets higher, wavelength gets shorter. Very good. Yes. Who needs an extra copy of this page? Can you pass this to Billy and Justin, Daniel, Tatum, and Misha? Anybody else who needs a copy of this? Can we pass this to Gabriel, please? Can we pass one to Michaela also, please? Anybody else who needs a copy of this? Okay. So guys, so remember, these are electromagnetic radiations. Is that right? All these waves that we learned are electromagnetic radiations. Now, generally Generally, waves need a medium to travel. Now, you guys are able to hear me because air is the medium. Is that right? The vibrations in air, as I'm speaking, transmit the vibration to the membrane in your ear, and that's how you can hear me. Is that right? But then electromagnetic waves do not need a medium. They can travel without a medium or in vacuum. Now, all of them travel at the same speed. All right? Every electromagnetic radiation has a speed which we call as the speed of light. All right? It's fixed. It's 3.00 times 10 to the 8 meters per second. We're going to record this in our paper, so know that. All right? All the electromagnetic waves travel at the speed of light. All right? What is the speed of light? 3.00 times 10 to the 8 meters per second. Since they all travel at the same speed, if the frequency is higher, the wavelength is lower. The wavelength is lower, the frequency is higher. And how are they related? C equals lambda times mu. Where what does C stand for? C stands for speed of light. Speed of light. Speed means how much distance does it travel per second. If you get sunlight, what is the speed of that light? All these electromagnetic radiations are also coming from there. What does lambda stand for? Wavelength. All right, wavelength. You can give wavelength in meters. Generally, it isn't given in what unit? In nanometers. And what's the conversion factor? We'll come back to that again. 10 to the 9. Nano means 10 to the 9. What is, this is nu. This is lambda, right? What does nu stand for? Frequency. All right, nu stands for frequency. And frequency units are what? Hertz, right?
Yes.
Frequency is nothing but 1 over second. Is that right?
Wait, nano is
10 to the 9. Nano means 10 to the 9. Mega means 10 to the 6. Milli means 10 to the 3. All right? These are metric conversion factors. Now, we just did this. Daniel was asking, where do I write this? So you can write radio waves here. All right? And you can go down the list. And what is the last one? Gamma rays. Okay? So that's the whole list. What did we say will happen to the energy if the frequency increases? It will increase. Now they are related by an equation E equals h nu. How are energy and frequency related? By the equation E equals h times nu. Where what does h stand for? It stands for Planck's constant. Now Max Planck was the scientist who provided us with Planck's constant. Anybody know what did Planck say? You guys presented scientists. Anybody remember what was Max Planck's contribution? Max Planck said energy is quantized. What did Max Planck say? Energy is quantized. Energy is transmitted in small packets called quanta. All right? So to give you an example, all right? Heat energy, when we heat something up, okay? Energy is transmitted, is that right? When we heat something up. What do we think? We think the energy is transmitted continuously. We think there is no gap in the transmission of energy. But is energy actually transmitted like this? No. It's in the form of discrete packets called quanta. That's how energy increases. All right? So small packets of energy are transmitted. That's the contribution of Max Planck, and that's where the Max Planck's constant comes from. Now, E stands for energy. Units of energy are joules. Nu here stands for frequency, and units are hertz. Now, so let's go to the visible region of the spectrum. In the electromagnetic spectrum, we human beings are very limited in our ability to see. Is that right?
Yes.
We can only see the visible region of the spectrum. If waves are given out in other regions, then we are not able to see them. Having said that, all right, and if this is the spectrum, we have invisible is Roy G. Bibb, all right, and these are how the colors are arranged in the electromagnetic spectrum. Are you with me? Then, which will you say has the longest wavelength? Which color will have longest wavelength? Red. And which will have the highest frequency? Violet. Now, you kids did a light lab last class. You burned stuff, and then you also looked through a hydrogen gas tube. Is that right? Now, why do these substances give off color? Now, before I go to that, let me show a few things. So let's see if I have, what is this? These are microwaves. So how do microwaves play a part? All right? So you have to turn on the microwave. So when the waves travel in your microwave, what molecule is that? Water. So the molecules vibrate with the waves. And what is temperature's definition? What is temperature? Average kinetic energy due to movement. Is that right? Yes. So as you increase the frequency of the wave, of course in the microwave region of the spectrum, what happens to the temperature? It increases because now the molecule is being hit more often with the microwave particle. Do you understand the theory behind microwaves? So it's very interesting to note that it's the rotational aspect of the molecule that the microwaves change. What do they do to your water molecules in the food? They start rotating those molecules when they hit them. When the molecules start to rotate, the food heats up. Alright? Everything that we eat contains water in it. And it hits only the water molecules. Now, let's look at this one. What is this? Radio waves. Alright? So, how are you able to get a signal? Alright? Let's do a reset. Where is the reset? Okay? Alright, say I can't see the reset. Alright? So this is an electron. What happens is, when the radio wave is sending a signal, let's just talk about one electron, which is so very tiny. Alright? When that one electron starts to vibrate, it sends this frequency of radio wave. Does that make sense? What does it do? This is your house. What does it do to an electron in your house? It starts to vibrate at the same frequency. Does that make sense? So a bunch of those electrons that are vibrating at that different frequency now gets converted back to what? The electrical signal gets converted back to what? To sound. Is that right? And we are able to hear it. Does that make sense? The vibrations sync with each other. The vibrations of the electrons. Alright? It gets transmitted. The sound, that what you're speaking at the radio station first gets converted, the sound waves convert to electrical signals. Electrical signals are transmitted as electromagnetic waves. They get converted back to sound waves. Does that make sense? How you're able to listen? Yes.
Wait, so if like before any radios were created, were there radio waves?
Yeah, the radio waves are already there. Like they exist, all right? It's just that we have to be able to get them, right? Okay, now let's move on. Shh.
So what is
So-
radio wave when it's not emission? Like before the radio was a thing, what really was?
We just needed to convert the radio waves back to sound waves for us to be able to hear it.
Yeah, what were radio waves before that? They were just like waves.
The waves travel with all different speed and things like that. They are there. You just have to be able to convert them into sound waves for you to be able to hear them, right? Does that make sense? Unless it's sound, it's converted back to sound, and it travels through air, and it can hear your eardrum, you will not be able to listen to it. Right? Does it make sense? It's all with respect to us. What can we do? It has to be in a language that we understand. Does that make sense? Okay. So, you did the hydrogen discharge lamp last class. Is that right? Let's just do one atom. So, if it is one atom, when the lamp gets lit, alright, when I'm switching the electricity on, what is happening? So, it's hitting and then you see the colored light. Is that right? And it's just one single one, and I'm not able to see the spectrum. So if I have multiple atoms, are you with me? Multiple hydrogen atoms, is this hydrogen, this is mercury, alright? Then you're able to see the distinct colors. Does that make sense? With multiple giving out all these lights. Now let's try and understand this. Okay, so some substances give off colored light. Some substances, like all substances, when you heat them, do absorb the heat energy. Do absorb the energy, right? Energy will get transmitted. But then only some of them show color. Why? You should be able to explain it at the atomic level. I want all my kids to draw an atom. Alright? Let's just assume this is a hydrogen atom. What is this? This is a hydrogen atom. And this is the nucleus. Alright? The central part is the nucleus. And the nucleus is positive, and it will, of course, attract the negative electron. Are you with me? So understand this. Let's say Tiana is the nucleus. Let's assume I am the electron. Tiana will try to pull me in, right? Tiana is trying to attract me. So this is the energy level. When I'm closer to Tiana, I have lesser energy, but if I'm moving away from Tiana while she's trying to pull me in, do I need more energy to stay away from her while she's pulling me in? Does that make sense? So, this is your lowest energy level. The one that's closest to the nucleus is the lowest in energy. As you move away from the nucleus, the energy becomes higher and higher. So for a hydrogen atom, this lowest energy state is called what? It's called the ground state, and it is lowest in energy. Alright? The other energy levels, now we can draw a maximum of 7 as we know it from the periodic table. Is that right? So these are called the excited states. Alright? So whether whether the hydrogen gas is inside a gas tube, or instead of the hydrogen, say you have a copper atom that you're trying to put into the Bunsen burner. Are you with me? As you are heating the substance, whether through electricity or through a Bunsen burner. This is a Bunsen burner, okay? In case you're wondering, does the energy move to the electron? Does it absorb the energy? Yes or no? Heat energy gets transmitted, so what will this electron do? It will kind of absorb this energy. Does that make sense? Once it absorbs the heat energy, what will the electron do? It will move from the ground state to the excited state. It absorbs the heat energy and moves. Now, for anything that becomes hot, it's a fact that it will also lose its energy. Is that right? Because the surrounding is cold. Yes or no? So what this electron will do is, even though because of the flame it's been excited to a higher level, it will not stay in its excited state for long. What will that electron do? It will jump back to the ground state. When it goes back to the ground state, what does it do? It releases the energy. Going up to a higher energy, it absorbs energy. Is that right? Going down, what does it do? It releases the energy. How? When it absorbs, it is heat energy. Yes or no? Are you with me? From the Bunsen burner or from the electric energy, that's the energy that the electron is getting. But when it releases it in the form of what energy? Light energy. Are you with me? Alright? If that particular atom releases the energy in the visible region of the spectrum, are you with me? Then we see that as a substance that produces color, light. Now all substances heat up. All substances, when you heat them up, they absorb the energy. They will all release that extra energy that they've absorbed also. But will all of them produce colored light? No. Only the ones that release energy in the visible region of the spectrum. We will be able to see them as substances that produce color. Does that make sense? Yes, Daniel. Heat is getting converted to light by that particular substance. Does that make sense? Are you with me? So there is one more thing you need to know. Alright? What we did was, we tried to split the color. Is that right? Now for copper we got a green color. When we looked at the hydrogen lamp, it was kind of pink. Can I say that? Kind of purplish pink. The lamp, the gas inside itself. When we tried to pass it through a prism, did it split into its colors? Is that right? Now these colored lines are very, very unique to a given element. Each and every element, it's like a signature for an element. Alright? So scientists know that the sun that we revolve around, is made of mostly hydrogen and helium. How the heck do they know that? Because sun is such a hot object. Nobody can go near it. So how did they determine that it's made of hydrogen and helium? So what they've done is, they've taken the spectrum of the light that comes from the sun, and they have analyzed the spectrum, and it resembles which two elements? Hydrogen and helium. That's how they know that sun is made of hydrogen and helium. It's very useful in identifying an element. It's like its signature. Does that make sense? Okay. We're going to go back. So guys, this this is the theory behind the lab that you did. And you kids should be able to explain this. Are we good? When you get a lab test on Tuesday, you should know this information. Are we good? Okay. So the next thing you need to know is you need to be able to do problems using the two equations that we learned. What were the two equations that we learned? C equals lambda nu, E equals H nu. Alright? So before that, we should know how to convert nanometers to meters back and forth. Alright? Why should we know to convert between nanometers and meters? Now remember, wavelength is it's so short that you generally give it in which units? In nanometers. But then, what is the speed with which light travels? Meters. So when you use that equation, C equals lambda nu, do you think you can have wavelength in nanometers in that equation? No. So wavelength in nanometers must always be converted to meters before it's substituted into your equation. Is that clear? Now, nanometers are generally numbers like this. Okay? So, I don't know, maybe I should do it in the bottom so that you kids can actually see this real clearly. Alright? 650 nanometers. Can I rewrite this in scientific notation as 6.50 times 10 to the 2 nanometers? Is it written in scientific notation? Is that right? Have I moved the decimal over 2 places? Am I multiplying it by 100? Yes or no? 6.50 times 100 is 650, correct? Everybody good with this conversion factor? I'm trying to convert the nanometers to meters. What do I know? How many nanometers makes a meter? 10 to the 9 nanometers is 1 meter. Is that right? Or in other words, I need to get rid of nanometers, convert it to meters. 10 to the 9 nanometers is 1 meter. Correct? Yes or no? Right? Why is it 10 to the 2? 650, do you move the decimal over 2 places? It's 6.50 times 100. 100 is written as 10 to the 2. Okay? So now, if you go down, what can you write this as? 6.50 times 10 to the 2 times 10 to the negative 9. Yes or no? Because 10 to the 9 is in the denominator, which is nothing but 10 to the negative 9. That's the same thing, alright? So what is, if you have a power of 2 and a power of negative 9, what does that become? What do you do? Negative 7. So 6.50 times 10 to the negative 7 meters. So 650 nanometers is 6.50 times 10 to the negative 7 meters. Are we good? Do we understand this?
Yes.
Okay, moving up. Let's look at this problem. So 650 became 6.50 times 10 to the negative 7 meters. Is that right? Now I have 575 nanometers. What do you think that will be in meters? What do you think that will be in meters? 5.75 times 10 to the negative 7 in meters, correct? Correct? Now the wavelength is in meters. What are we supposed to solve for? Frequency. What equation will we use? C equals lambda nu. Lambda times nu. What is the value of C, or speed of light? It's always constant. It's always 3.00 times 10 to the 8 meters per second. What is the wavelength? The wavelength is 5.75 times 10 to the negative 7. Should I have to keep it in meters? Right? Can I substitute in nanometers? No. Times nu. How do I solve for nu? It's a simple math equation. What do I divide both sides by? So if I divide both sides by 5.75 times 10 to the negative 7 meters, this will cancel. How do I put this in my calculator? How do I write this number in my calculator? I do 3E8, correct? Right? And how do I write this? 5.75 E negative 7. What is the answer? Can I see my students? You should know how to put this number in your calculator. Can somebody give me the answer? Three E8 divided by 5.75 E negative 7.
So you're dividing by this.
What is the answer? 5.22 times 10 to the 14. What are we solving for? What are we solving for?
Meters per second.
Frequency. So what is the unit? Hertz. All right? That is my final answer. Do we see that? What the heck is this kid on? All right? Are we good? 10 to the 14. If you put it in your calculator, you should be able to see that answer.
And that is the reason.
That is the nu or frequency. All right? It's like a slanted V, right? Now, all of these problems are really easy. I would like you to go home and try them. All right? I've given you two problem sheets. I'm going to do one more problem with you, and then the remaining you want to go home and try on your own to see that you get them. All right? I'm going to do number 14 now. All right? In number 14, what is given to you? What is given? What value is given?
Energy.
Energy is given. If energy is given, which equation will you use first? E equals? Alright, so if I have E equals H nu, what can I solve for if I'm given energy in this equation? What can I solve for? What is energy? Energy is 4.30 E negative 19. Is that correct? Energy equals, do we know what Planck's constant is? Do we know the value of H or what is Planck's constant?
Yeah.
What is it?
6.63.
6.63 e to the negative 34. What is it that we don't know? Huh? That this is a constant, remember? Like C, if you look at E equals H nu, is the value of the constant given to you. It's always the same number. What can you solve for? Can you solve for frequency? Right? What is the value of frequency here? Can somebody tell me what is frequency? What do you do on both sides? Divide by Planck's constant, correct? What is frequency? Can somebody tell me what that answer is? What is it? 6.49 times 10 to the 24 hertz. Is that right? Okay. They want you to tell you what the color of the light is. In order to determine color, what should you find? Huh? What should you find? Wavelength. So now I know frequency. How do I find wavelength? What equation will I use? What equation will I use if I need to find wavelength? So I'll use the equation C equals lambda times nu. What is the value of C? What is C, guys? 3.00 times 10 to the or E8. Alright? 3.00 E8 equals, I don't know my lambda, what's my frequency? 6.49 times or E24, right? 6.49 E24. What is my wavelength? What is my wavelength? .62 times 10 to the negative 7. What are the units if I'm using the equation?
17. Negative 17.
Are you sure? It cannot be negative 17. Is it that high?
Well, because the first time is supposed to be 6.4 times 10 to the 14.
Oh, it's supposed to be 14. So this is 10 to the negative 7. Is that right? Okay. So what are the units of wavelength if I'm in the equation? Wavelength after I solve the equation, will it be meters or nanometers? If I'm getting it from the equation, what is it? Meters or nanometers? This was meters per second, right? This was per second. So what do I get wavelength in? Meters. But look at my standard values. They're given in what units? So what is this in nanometers? What is 4.62 times 10 to the negative 7 in nanometers? Is it 462 nanometers? Correct? Is that right? What color light does it match with? Well, indigo is no longer considered as a color. So, what is the color of the light? Blue. Scientists no longer consider that to be a special color in the spectrum. They say it's a shade of yellow. That's all. It's blue and then violet. Yeah, there is no indigo. Blue is there. Indigo is not there anymore. Okay? Do we understand this problem? Does it combine both your equations? Do we understand this? All right? So yes, Ali.
So how do you know which color to pick?
In the range is fine. In the range, I wouldn't mark you down if you put indigo also. It's in the range closest. All right? Or if such a question is asked, we'll give you a whole range of color that could be blue. Does that make sense?
Oh, you would give us a range.
A range instead of giving a single number. We'll be more specific.
Why do you write 6.49?
No, that's 14, not 44. That 24 was, that is 14. Somebody gave me the answer wrong. So I got that. I wasn't substituting, Natalie.
So how did you find that?
Which one? So this is a simple straight equation, Natalie. This is x. This times x. How do I find x? You divide by this number on both sides, correct? And that's how I got that answer. Are we good? Do we understand? So I'm going to stop my recording at this point so that... What happened to my recording?
It's never recorded.
What? Okay, it is recording, guys. Let's stop.